Hello and welcome to this presentation by QED, Quantum Electrodynamics. Today we'll be discussing the VEM drive, the Variable Electromagnetic Drive. It's a revolutionary transportation technology with the potential to transform how cargo and humans travel from Earth into space and beyond. My name is Kyle Finley and I'm excited to take you through this concept today. First, let's look at the team behind this ambitious project. At the core of our research is dppares, the primary inventor of the VEM drive. Dave brings decades of experience from the Air Force and defense contracting, and he's also a professor across multiple disciplines including meteorology, astronomy, earth science, and physics. As for myself, I'm Kyle Finley, the CEO of this initiative. I hold degrees in native studies, computer engineering, information assurance, and a master's in IT innovation. Alongside my technical background, I bring expertise in programming, graphic design, and engineering to the table. Our electrical engineer is James McVeigh, a professional with 38 years of experience designing and consulting on custom electronics. Our final core team member is Reed Sherman, our community engagement officer with a background in aerospace and engineering, along with service in the Civil Air Patrol. The problem with space travel. Space travel is notoriously difficult due to the vast distances. Here we will see a chart showing engines and the time it takes to travel to celestial objects such as the Moon, Mars, Pluto, and Proxima Centauri, the closest solar system to our solar system. Take the Moon at 200,000 miles away. Most spacecraft can reach it in a few days. But for Mars, even advanced propulsion systems like NASA's Dawn mission took 260 days, while SpaceX Starship is estimated a 90-day journey. Using the VEM drive, however, we expect to achieve Mars travel in as little as 6 days. When it comes to Pluto, which conventional systems can't reach within a year, our VEM drive aims to reach it in just 146 days. Our goal is to make deep space exploration practical within years, not centuries, by leveraging this breakthrough in space travel technology. And lastly, we can see the years it would take for conventional space engines to get to the closest solar system. While not proven yet, our VEM drive may be able to travel close or surpass the speed of light. This is due to a fundamental design difference that our device uses as opposed to conventional space traveling means that everyone else uses. But we can see that long-distance space travel begins to take shape with our VEM drive. So let's talk about VEM drives. Advantages of the VEM drive over ion and Hall effect thrusters. 1. It's fully powered by DC energy. This means it can be completely powered by batteries, solar, nuclear, or other electrical generators. That's not true of other engines. 2. It's propellantless. It does not need to be refueled like all other engines. 3. It has higher theoretical speeds. It can reach speeds far beyond other engines, possibly up to the speed of light or beyond. 4. Its compact and scalable design. It means it can be used in small satellite designs or larger vehicles. And 5. Heat-free, solid-state design. The VEM drive is solid-state, thus increasing its lifespan. And to the right, we see Model 13 that can be used for satellites. It's our 1-foot model. And here, our 3-foot model using double fractal array design. Here's a model, 21A, which is used in a quad setup where it can be rotated to look at the field effects at different angles. And here's another Model 13 that can be used for satellites. Alright, now we'll go over milestones completed. Here we have a picture of the tripole fields and the warp core at the center. So scientific proof for the VEM drive. We have 1. Proof of concept experiments, including the interferometer experiment. This is the experiment that we see to the right where a laser is shot through the tripole fields and we see the field effects creating the fringe patterns that have been changed between it being on and being off. 2 is our force of measurement and force validation experiments. The force versus power experiments show us the connection between the power given to the system and the amount of force that is created from the system. 3. Prototype development and iterative testing. Models 13 to models 23 show us that we have various models of various sizes and each of them perform differently, but we're able to change the shape and size of these to fit the needs necessary. And 4. Verification through controlled experiments, such as the Cavendish experiment. This verifies gravitational effects without the interference from magnetic fields, wind, or change in wire temperatures. All in all, there's a plethora of evidence behind these devices showing that they work and that they can be replicated. Alright, now we'll look at the market opportunities. Here we're looking at a comparison between existing and potential market growth in the space industry sectors. The blue is existing and the orange is potential growth. We plan to target satellite services as the first, as that is the largest existing market currently. While we're not providing satellite services such as GPS or internet, we'd be providing service to those services, and that can be seen in the first bars on the graph with a market cap at $120 billion in 2023. Satellite services is the largest industry, but our main sectors that we could greatly profit from are in 1. Launch services. The VEM drive can eventually replace chemical rockets, providing cheaper and safer launches. 2. Space exploration. VEM drives are far superior in that they are cheaper, faster, and more sustainable than other known means. And 3. Asteroid mining. The VEM drive's speed and durability make it ideal for collecting and transporting resources from the asteroid belt back to Earth. In summary, there's a $12 billion market currently in 2023 in space, and in the future we're looking at a $70 billion market in the next few years that are up for grabs. This is on top of supplementing the $120 to $150 billion market in satellites, meaning there's plenty of room to grow for our company, and with this product we would easily be able to outcompete the competition. Now we'll look at our first goal. Phase 1 is implementing the VEM drive into satellite operations. VEM uses for satellites. 1 is maintenance and longevity. Satellites with electric engines free from fuel limitations could double their operational life by allowing continuous orbital adjustments. This avoids replacement launches, eliminates propulsion system failures, and boosts savings by 100%. 2. Productivity increased. For imaging and communications, you could reposition the satellite frequently to service high-priority targets more often. And that means that you have more services to sell customers for the time you are in orbit. You could also fly in lower orbits, which increases the data bandwidth available. This could increase profits by 50%. Now we'll look at the financials behind Phase 1. Here's a chart showing Phase 1 earnings and saving differences on satellites. This chart shows different sizes of the satellites on the left in the satellite types, the weight ranges in the second column, an example cost in that size in the third column, increased performance earning estimates, that's our 50% bonus for being more maneuverable and going to lower orbits, extended life-saving estimates, and finally the multiplied profit of those two fields combined. We'll go through two examples. The first section we plan to target is the cube satellite market, which ranges from 1U to 16U. If the satellite is $50,000, then the estimated increase in earnings would be around $25,000. The extended life would save you from having to send a second satellite up, saving another $50,000. And finally, an increased profit from the performance boost and the extended life would earn around $150,000. This basically means that with a longer lifespan and the performance boost, one satellite could do the job of 3 satellites. If we look at high complexity satellites like the Hubble or James Webb Space Telescopes, we see that a $1 billion satellite could have a boosted performance worth $500 million, an extended life worth $1 billion, and a total increased performance worth about $3 billion. Generally, these figures change greatly depending on what the satellite's exact function and size are, but these figures should give you an idea of the impact of our technology in the field. Our second goal, or phase 2, would be creating a spaceport. 1. A single spaceport can replace cargo transportation from airplanes and ships to any location on Earth provided there is a landing area. 2. It can also transport humans to space in a quick and convenient method. And 3. It can bring in materials from space and send cargo to space for long-distance missions. Now for the financial chart. On this one, we're just going to be looking at the launches from Earth to space. So here we have a chart showing the Phase 2 savings on a $60 million SpaceX launch. Here we have the cost type again, as seen on the previous chart, and the percent total of the cost that it takes to launch. So we see a majority of this is eaten up in the launch vehicle production and ops at 65%. So this is one area we would target. 80% of that is in propulsion systems and tanks to hold fuel. So with the VEM drive, we would be able to eliminate pretty much all of that. We don't use any fuel, and our structure is a lot easier and cheaper to make and to power. The second area is in the propellant, which is 3% of the total cost. But we would completely eliminate that, so that would save around $2 million. And the third area is mission assurance and insurance. It's at about 7.5% of the total, and we would be able to save about $500,000 on that because these launches would be a lot safer, and there's a less chance for them to go wrong since they're a lot more controlled going up. So in total, we would save about $30 million per launch out of the $60 million that it's currently at. In 30 launches, we would save almost $1 billion out of the $1.8 billion, so about 50%. We're pretty close to the 50% savings on these ones because the launch is a very large cost to all these operations. Other uses. One other use is artificial gravity for long-term space travel. So you can put some of our VEM drives in the floor of a spacecraft to generate a single dose of gravity to pull people to the ground, or to hold water in cups and to give people some exercise as they move around on the ship. So this would eliminate a lot of other things people are trying to do. Such as having exercise machines or having gravity produced from rotating the space station to artificially produce gravity and stuff like that. We'd be able to do it with just a few of these devices with 20 to 30 watts of power, just enough to hold you down and pull everything and keep everything in place basically. And they'd be able to be turned on or off with a flip of a switch. The second use is terrestrial travel using a monocraft that we came up with. If you put these drives onto a craft like this with enough force and a good battery, you should be able to fly around on the planet using multiple VEM drives to manipulate the field around the craft. So you'd be able to go up, down, left, right, any direction you want to go, you'd be able to fly around. We have also tested that there have been no side effects to being around these drives for humans, and we've also done fly testing where it shows no adverse effects on flies. We've also seen that there's no radiation coming from these devices, again making it useful for artificial gravity, or if you're going to be standing on a monopod, it should not be affecting humans in any way. A third use is space debris cleanup. If we created a gravity well using these devices, we should be able to suck in a lot of these little particles into a gravity well and then either shoot it back into Earth to have it burn up in the atmosphere or shoot it out into space. Or we could put these into a recycler and reuse the materials. Next, we'll be going over some of the past timeline. Here we'll be going over some of the past timeline of QED. So this is our timeline from 2012 to 2022. In 2012, that's when we really got started with our first confirmation experiment. So we were doing multiple experiments before this, but on October 15th, 2012 was when we had our first confirmation experiment with the interferometer. In 2018, we got our first paper published with the AIAA. It's the largest aerospace conference in North America. And in 2021, we got our first video recorded with movement directly recorded with video. So this is a direct observation recorded of the VEM drive with movement on a camera. And this is all posted online on YouTube. And now in 2022, and beyond, we're looking to get funding to finish the prototype for our next future timeline, which we'll look at next. This is our future timeline. Here we're looking at in 2025 of building a lab. A lab is needed for standardized research and progress, which will take a year to finish. And in 2027, we'd be looking at finishing the prototype, which would be able to start providing services and working on revenue. This would be the Phase 1 satellite implementation that we have just talked about. In 2028, we'd be looking at working on a larger model for spacecraft integration. Once that's done, we would then be integrating that larger model into spacecraft that can take humans into space. And in 2030, we would start doing a spaceport construction for Phase 2. In 2035, we would like to have the spacecraft complete, so this would allow for us to start taking things into space and bringing them back. In 2040, we would like to have completed a spaceport that could service anywhere in the world by lifting stuff off from the spaceport and landing wherever it needed to land. And then providing the services of transport either to space or to other places on the planet. And that brings us to our call of action. So QED has 3 phases here. The first phase is $5 million over 3 years. We're looking at completing a VEM production lab, which will help us complete these engines for commercial use. We want to do satellite testing of the VEM drive to make sure it integrates into the satellites correctly and can be used for station keeping and other services. Our MVP will be completed for a small revenue, so once the MVP is completed, we can start putting these on satellites and bringing in revenue that way. Phase 2, we're looking at $50 million over 5 years. This would complete a functional Earth-to-space VEM drive, which will allow for us to sell services for lifting cargo to space, which will bring in a lot more revenue, as we've seen before. We would also have to get government approval and restricted airspace to start doing this phase. For the last phase, Phase 3, we're looking at $500 million over 10 years. This will help us complete a spaceport on Earth for VEM drives that would allow us for large-scale craft that can take people to space and bring them back. And we'd be looking at doing long-distance space missions beyond the solar system or to the asteroid belt. In conclusion, we are at a pivotal moment in advancing a breakthrough space technology system. To make this vision a reality, we need your support. Your contribution will not only help us achieve these ambitious goals, phases that transform space travel and exploration, but also position us to create a sustainable revenue stream and drive innovation that impacts the future of humanity in space. Join us in this journey to redefine what is possible. Together we can propel the world into the next era of space exploration. Thank you for watching this presentation by QED, Quantum Electrodynamics, on the VEM drive, Variable Electromagnetic Drive. Please contact us if you are interested in working with us on the project, and have a nice day.